Hello, welcome students. So we are starting chapter 13 and we're continuing with the theme of structure determination. We've already covered mass spec and IR spectroscopy, and we're going into the realm of NMR spectroscopy. So to me, this is the most powerful method of confirming a structure that you think you've made. Maybe you've run a reaction and you want to make sure that you made what you think you made. Assessing the identity of a compound, maybe an unknown. And we're going to do this with two different methods. One is called proton NMR and the other is called carbon or C13 NMR. So this is going to be broken up into three different parts. The first part is just getting you to understand what is NMR in general, how it works, just how the spectrum looks like. We'll talk a little bit about chemical shifts, information about different peaks, and then there's a lot more detail that we'll get into in the next few sections. So what is NMR spectroscopy? So first of all, it's an analytical technique. As I mentioned, you'll make a compound and you need a way to confirm identity. There are limitations with mass spec and IR, right? Maybe you get the mass of a compound, some fragmentation patterns, but still, you don't know the actual connectivity. Also, IR is usually giving you kind of a limited view, maybe confirming the presence of certain groups, certain types of bonds. So this is a more detailed approach. NMR stands for nucleomagnetic resonance, and I've already mentioned its uses. One thing that's really interesting is you can also analyze mixtures. I've been in a situation where I had a mixture of alkenes and I needed to tell the difference. You could quantify those. Also, I was working with 10-membered ring systems in graduate school, and there were different conformers. So if you can run NMR at really low temperatures, which you can, maybe minus 70 or minus 90 degrees C, you can actually freeze out different conformers. And sometimes you can actually assess the purity. Sometimes that's an issue, but there are usually other ways, better ways to assess purity. What info are you going to get out of the spectrum? There are three main pieces here. Chemical shift, it's going to be the x-axis on the spectrum, and it basically identifies the types of atoms or groups in the molecule you're looking at. So maybe this is confirming that it's present, that type of atom or group is present, or helping you discover a new compound in terms of identifying an unknown. We're going to later in part 2 talk about spin-spin coupling constants, which will help you find out what the neighboring or adjacent atoms are like. And signal intensity tells you how much, the number of specific atoms in a molecule. So you can see there's a lot of information here just from a simple spectrum, and they'll be useful in determining molecular structure. So how does this work? The first thing is we're focusing on proton NMR and C13 NMR because these are NMR active nuclei. They have a spin that can generate a magnetic moment. You have to think about atom and nuclei having a certain spin. Think of it as the Earth on its axis, and it could create a magnetic moment. So nuclei are positively charged and they'll interact with an external magnetic field. So in general, without a magnetic field, the magnetic rotation of a nuclei is just randomly oriented. However, if you do apply a magnetic field, the nuclei will align with it or against it. So if the magnetic field is applied in this direction, some of those nuclei will arrange aligned with it up in this direction or against it down in this direction. So you could think of this as up or down spins. So the one thing that is critical for us getting a nuclear, an NMR spectrum is basically there are different spins and these nuclei can do a spin flip. So when exposed to certain energy, certain frequency of the electromagnetic radiation spectrum, which happens to be the radio wave region, nuclei can absorb energy to cause a spin flip to go from that lower energy state to a higher one. And I'll show this better on the next slide. The frequency that can cause this resonance, and when we use resonance, we mean basically now the nuclei are flipping to now be in resonance with that applied magnetic field. It'll depend on a couple of things: the strength of that magnetic field, the nucleus that you're talking about, and also the electronic environment. So the reason why we get so much information is in a molecule, there is a different electronic environment as you go from different atoms to other atoms in different groups, because those atoms have a different number of electrons around it. And sometimes even with pi bonding, you have just different electronic placement. So here's a little bit of a better picture. Here are your two spin states. As you increase the applied magnetic field strength, you get a separation of these from a clear low energy state aligned with that magnetic field, or a high energy state aligned against that magnetic field. So energy can kick and allow for that spin flip. What the NMR spectrometer will do is, as this high energy state nuclei relaxes back to the low energy state, that releases energy in the form of a radio frequency that's measured. And that's what's processed to create your NMR spectrum. Okay, let me tell you here what it's like to run an NMR. Basically, this is your NMR machine here. This is where the magnet is. This is very large. This takes up a good part of a room, and this is taller than me. I have to have a little step stool to climb up here, and then on the top, insert my sample, which is in a glass tube through the bore in the center. There's a spectrometer that'll transmit and receive the radio frequency waves to help you make your NMR measurements. And then you have a computer that's going to process that, spit that out as a spectrum. A little bit more detailed, here is where you're going to put your sample in that top part of the center of the magnet. You basically have some organic compound, a sample that's you've run a reaction, you've purified, you've worked it up, maybe you had to do solvent extraction, you've purified it, and now you're ready to dissolve it and put it in a thin glass tube. You need a suitable solvent. So a lot of times this can be chloroform or maybe dimethyl sulfoxide. And then you'll place the tube here in the center of the magnet, and this will go down, it'll release down into the magnet. I actually had an accident once. That thin glass tube that you put in through a small hole, and one time there was a little bit of resistance and I was a little bit more forceful than I should have been, and the whole glass tube snapped and my finger slipped and it seriously sliced off a part of my finger. It was quite a bad accident. I had to go to the ER. I'm totally fine, and this is actually a very safe instrument to use. I haven't heard anyone else have that sort of accident, but it did happen. So anyway, anytime you're in the lab working with anything, when you work with glass, and especially any tubing or O-rings, be careful. Anytime there's resistance, just back off and try a different method, more passive method to insert something. Okay, so you insert your sample. A constant and varied strength of an applied magnetic field will cause each nucleus in that molecule to resonate at a slightly varied field strength. The absorption of that radio frequency energy will be monitored, and a detector will display that as a peak on your NMR spectrum. Okay. Before I get to the spectrum, let me just tell you, there are different absorption frequencies. We're going to look at one type of category, proton NMR, and then another category, C13 NMR. But basically, one thing that's common is there's a phenomena called shielding. So just think of just nuclei having a certain amount of electrons around it. depending on what kind of nuclei they are or are attached to. And so that will actually counteract the effect of this applied magnetic field. So the effect of that is you get this kind of effective magnetic field where it's the applied minus that local one. So the key thing I want you to know is that basically, depending on the nuclei that for example, proton is attached to, that electronic environment is going to be different depending on the connectivity of atoms and the type of atoms being connected to. So you'll have different types of shielding. For example, if you have an electronegative element, that'll pull electron density away, so there's less shielding. So less of that B local, so B effective will be greater. The consequence of that is when you have your spectrum, you'll be further towards this side of the spectrum. This is called downfield, where there's less shielding. So let me just break this down. This top spectrum is a proton NMR spectrum of methyl acetate, shown here. The lower spectrum, B, is the carbon, the C13 NMR spectrum. So just focusing on the proton NMR, what the proton NMR spectrum will give you are peaks corresponding to the different types of protons. So it's not going to give you info about the different types of oxygens. It's only spitting out a peak for the different types of hydrogens. So look at this molecule here. You have a methyl group here attached to a carbonyl and a methyl group here attached to an oxygen. You may at first glance just look at methyl, and just say, oh, they're the same, identical. But the environment is different. So that's what's key in interpreting NMR. Look at the environment. These hydrogens are attached to a carbon that's next to an O, a very electronegative element. These three hydrogens on this carbon are attached to a C. And yes, it's a carbonyl C, but still, it's not as electronegative an element as the oxygen. So this H in red, even though there's three, there's three identical ones in the similar environment or the same environment. That'll show up more downfield than the green H's here, just attached to a carbon attached to a C, which will show up around 2 versus a little around maybe 3.7 here. Okay, if we go then and look at the carbon, C13 NMR, that then is going to tell you the different types of carbons in the molecule. So a lot of times, if I'm going to make a compound, if I made a new one, I'm going to take both a proton NMR and a carbon NMR to help confirm the identity. Here, if I look at the molecule, I have three different types of carbon because I have this methyl attached to a carbonyl group. I have a carbon that is a carbonyl carbon, doubly bonded to an oxygen and even attached to an O, and then this carbon just attached to an O. So the one that will be most downfield is this one. It's attached to 2 O's. It's part of a carbonyl group, so it'll be further downfield. Notice the scale is different. We'll talk more about that later. The next one over is this green one, again, attached to a more electronegative element, the O. So it comes up around 50 for the carbon NMR. And then the last one is this guy here, the blue guy, which will then show up further upfield. Okay. So let's just practice first, just basically identifying different types of protons in a molecule. So take a look here. We have 2-chloropropene. Think about how many different types of H's you see. So you have this to consider. How many different ones do you see? Okay, so here's our solution. There are 3. 3 different types of protons. Some, you may have thought that these were identical, but be very careful because this HC is cis to this chlorine, but this HB is trans. You know that those are different environments because there's just different proximity to that chlorine here. So the H is on this methyl, those are identical, that's one type, and then each of these vinylic guys. So a total of 3. So we would expect to see 3 different peaks in the proton NMR. Let's take a look at the spectrum. I want to just really now show you on the x-axis is what's called chemical shift. And basically the downfield region is here towards the left, and you know they're relative. More towards the left is downfield, more towards the right is upfield. Downfield is deshielded. We also call that low field. Upfield is shielded and it's high field. Okay, so for example, those that are downfield, the nuclei absorbing on the downfield have less shielding as they require they require a lower field for resistance. The right segment is upfield, and the nuclei absorbing in this region have more shielding as they require a higher field strength for resistance. The chemical shift here, their numbers 0 to here 10, and basically there is a scale. It's called the delta scale. The chemical shift is given this delta symbol, and you don't need to know the details of this, but basically I want to tell you this is done so that we can kind of calibrate this across various different types of NMR machines that may have different types of field strength. So it's basically the observed chemical shift, which is the number of hertz away from the TMS group. So here's our TMS peak. This is the calibration peak that's set at 0. TMS stands for trimethylsilane. So you have this molecule and it's the H here that shows that. That's a reference peak. And that's divided by the spectrometer frequency in megahertz. What you are responsible for is really just understanding the different regions where these peaks are going to show up. So protons bonded to saturated sp3 hybridized carbons absorb at a higher field, upfield. So they're in this region. Protons bonded to sp2 hybridized carbons are at lower fields because of the pi bonding. Protons bonded to electronegative atoms, we'll find them basically more in this region here. And I'm going to give a more detailed region, but lower field. This is what you need to be responsible for, regions of the NMR spectrum where certain groups show up. So sp2 hybridized carbon, when there's aromaticity, it's at a more downfield. When it's just vinylic, it's in this range, 4.5 to 6.5. If you have a carbon attached to an N or an O, a hydrogen off that carbon will be in this range, so centered around 3.5. Allylic, so it's not vinylic, it's not directly attached to a double bond, but on the next carbon over, an sp3 carbon next door, it'll be in the 2 range, and then saturated is more upfield. So that's what you need to get in your mind, kind of categorize these areas to the types of H's, the types of environment those different H's are on. I'm going to end this segment with just one example. We're going to take a look here at tert-butyl methyl ether. And I want you to look at this molecule, study it, think about the different types of hydrogens in here, how many different environments are the hydrogens in, and how many proton NMR peaks you expect in the NMR spectrum. And then determine the general location of where those absorptions will be. Okay, so first of all, you should have come up with 2 different types. The methyls on the tert-butyl, those are identical, so that's one type. The methyl H's, the methyl H's off tert-butyl are 1. The methyl H's off this C connected to the electronegative O is another type. So those are 2. If you go back to that chart, you can see tert-butyl will have a hydrogen off of a carbon, that's sp3, so it'll be around 1-ish. The CO with the H's attached to that methyl group, those will be more downfield in the 3.5 range. So you should be able to be given a molecule and have a general feel for how many peaks are going to show up and roughly where in that spectrum, 0 to 10, those peaks will show up. Given the actual spectrum, you can actually assign these. So here's this actual spectrum. There's a peak around 1.2, and there's another peak around 3.2. So that 3.21, sorry, I totally messed this up. This is switched, I apologize, and I'll correct that on the slides, but you know that the O-methyl is around 3.5, so this is the O-methyl one, not tert-butyl. And then the 1.2 is the tert-butyl one. So I apologize, I'm going to correct that. But you can see that here, the tert-butyl is around the 1, the O-methyl is around 3.5. Here it comes up at 3.2. Okay, you will also need to be doing the opposite. Given a spectrum that's not labeled, can you, given additional information and the molecular formula, come up with a structure perhaps? Okay, I'm going to end here, and we'll continue with the next two parts soon.